Okay, welcome to Robotics 2. In last class, we looked at something called as the dynamic observer theory. We also looked at what it means to estimate a quantity. Then we looked at Kalman filter. And then I skipped through 10 slides of math. And the reason for that is math of Kalman filter is quite intense. So this involves stochastic calculus, stochastic partial differential equations, equating their first derivative to 0, and so on and so forth. And then you land up with covariance update and all that stuff. But what I want to do in this class is I want to devote completely to Kalman filtering without significant mathematics. So I'm going to call this sort of Kalman filter for someone like me who is mathematically challenged. So I will try to explain this Kalman filter process in simple words. And I would actually work out a simple example. And I would strongly recommend that you work out this example with me so that the Kalman filter will be clear to you. So I'm going to call today's lecture is Kalman filter for mechanical engineers or robotics engineers, mechanical robotics engineers. And fundamental purpose of today's lecture is to explain what Kalman filtering is, so that if a high school students ask you, hey, what is this Kalman filter? You may be able to take pen and paper and explain what Kalman filter is. And I will try to use the high school algebra to derive the Kalman filter equations. So nevertheless, today's lesson is super duper important. So first and foremost, let me answer this question, why? Why do we need Kalman filter? Suppose we have a signal, okay? We have a signal and that signal is super noisy signal. You have an image that is noisy, which means that has blurred. Or if you have the CAD model or a scan that is noisy. So how would you convert this noisy signal into something meaningful measurement? So how do you convert this noisy signal into meaningful measurement? Now, traditionally one can say, hey, if we have a noisy signal, so you have this noise, just do some sort of low pass filtering. So use a filter and hopefully we would get clean signal. And this approach sometimes may work, but many a times it does not work, especially when your signal or the quantity that you are trying to find out is derived from some multiple sensors, derived from multiple sensors. So think about it like you have one sensor and you have another sensor. So clearly these sensors have different properties. So you cannot combine these two sensors together. And the underlying quantity that you are trying to measure, say if you're trying to measure, say, intensity of light. And to be honest with you, intensity of light itself is changing. And even the changes are small. but it's not constant. It's slightly flickering. So how do you combine noise in process, noise in measurement, and get an accurate estimate of light intensity? Same thing happens with filters. Or pictures, or images, or scanned models, or radar data, or the local GPS. So to give you an idea, Kalman filter, it's considered as the one of the greatest discovery, one of the greatest discovery of 20th century. Apollo 11 mission used Kalman filter. And this is a achievement because at that time we did not have, as a matter of fact, I was not born. So at that time, we did not have supercomputers. We did not have the computation power, that is algorithm, to get the accurate measurement. The sensors, we did not have MEMS technology. It's a very, very important thing. Very, very important thing. Important algorithm. And that's what it is. It is an algorithm. When we say filter, it's not a filter in a sense, but it is a smart way of combining more noisy variables. So mathematically, what you have is, whenever you have a noisy measurement, you have something called as the Gaussian distribution. So what you have is, and I'm sure you studied Gaussian distribution in statistics. So you have a mean and you have a standard deviation or variance. So now let's understand, you have a process that is Gaussian. Then you have a sensor or the measurement that is also Gaussian. And we are talking about the simple Kalman filter. So process, and you have this sensor. So you have two Gaussians, just to think about it. Now the question is, how do you combine these two Gaussians to get some sort of estimate that is accurate or optimal in some sense? And the thing is, you multiply. You multiply the process Gaussian, you multiply with the sensor Gaussian, and then you get a combined Gaussian. And that Gaussian may look exactly like these two, or maybe slightly different. And what you do is, you actually locate the mean of that Gaussian, mean of the combined Gaussian, and you say, this is my estimate. That is all Kalman filter is doing. A linear Kalman filter takes the noise in the process, noise in the sensor, multiply their probability density functions. I will call this P probability density functions or distributions, and finally finds the resultant and gives us an output that is around the mean of the resultant distribution. So this is the resulting distribution. This is the crux of Kalman filter. Everyone understood? This is what the Kalman filter is doing. Now, the equations are complicated. I will not lie to you. Equations are complicated. And when I saw Kalman filter, first time in my life, I was scared because at that time we did not have Simulink or MATLAB toolboxes. So I was like, wow, implementing this complicated algorithm is going to be very, very difficult. But as I looked at it more and more throughout last few years, something simple came out of those complicated mathematical equations. And I'm going to give you the basic sort of the meat and potatoes of Kalman filter. So what is this Kalman filter doing? So let me write down a very simple expression that is at the heart of Kalman filter. So I'm going to call this heart equation. Maybe I should draw heart equation. And this heart equation is something like this. Xk is equal to, I'm going to call this kk multiplied by zk plus 1 minus kk multiplied by x hat k minus 1. And at this point, I just want to show you that this equation, this is one gain and this is other gain. But if you add these two gains, so just a side note, if you add kk plus 1 minus kk, that gives you 1. So in other words, what is happening, it's this gain k is changing the weight on zk and xk. And let me give you a very simple example. Imagine if my kk, as an example, this is side, my kk is 0.5. Then it means I have 0.5 zk plus 1 minus 0.5, which is 0.5 x k minus 1. If I have kk at 0.25, then what it means is I have 0.25 zk plus 0.75 x k minus 1. So all the time, this kk, which is called as the Kalman gain or just the gain, that can change. So this is the Kalman gain at k. And this k can vary from 1, 2, 3, 4, 5, 6, all the way to 1,000, 10,000, infinity. So this Kalman gain is going to change. Now xk, and always remember, I'm going to add this hats. So hats indicate estimate. So hat means estimate, not actual value, but the best possible guess. Best guess. At any point of time, if you have any questions, just stop me and ask. So what we have here is, and this is the heart equation, wherein xk is the current estimate. Then zk is the current measured value. This is the current measured value. And x hat k minus 1 is the previous estimate. So what we are doing here is, if you think about the example, that you have a light source. You have a light source, and this light source is flickering or it is changing. And you have some sort of measurement device, maybe uh, some sort of an optical diode, or maybe some sort of illumination sensor, some sort of photoresistor that is giving you a measurement. So just think about it like you have a photoresistor and that is giving you the intensity of light. So what I'm going to do is every time I'm going to get the measurement from this photosensor, I'm going to call this ZK. And I'm going to have us in storage the previous estimate that I calculated. And you may ask me, what happens when we start? When we start, we don't have an estimate. So I can simply say when my K is 0 or 0 minus 1 or Kx is equal to 0, in these cases, my x hat is 0. So I start with 0 estimate. I'm going to start with 0 estimate, or I can start initialize at some random estimate. It does not matter. So I would start at some random estimate, but what's going to happen is as new value, new measurement comes in, I'm going to combine these two terms to find out the current estimate. Now what happens is this current estimate becomes the previous estimate in the next iteration. So this becomes xk minus 1 and I get another Zn. So this becomes the previous estimate and I repeat the process and I get new estimate. And what happens is these new estimates xk hat will continuously converge to the true values. So what it means is if I have this noise source, if I have this light source that is noisy, if I have this photodiode, so I'm going to call this a photodiode, and this is a light source. If I combine with this mathematical algorithm, then eventually I would get the true value. So if you see, if this is the true value, then I would get optimally, you will see that I will converge to the true value. So this is x hat and this is true value. And you will notice that this filter or this algorithm will take some time to converge, but at the end, this is what is going to happen. Okay, everyone understood the Hart equation? And some of you may ask that is it similar to the complementary filter? And the answer to that question is absolutely. If you look at the Hart equation, in the earlier cases, we combined accelerometers and gyroscope. We did the exact same technique. We had one measurement and we had another measurement and we combined those two measurements. But in this particular case, we have a measurement and we have a previous estimate. So now the key question is, how would you change value of K? Please note, this value of K is changing at every iteration. So which means K here will be different than K here. So this K and this K, they are going to be different. And how do you find out this K is again a matter of equations, and those equations will come as we discuss. So before I proceed to the next part, everyone understood why do we need Kalman filter? What exactly is happening mathematically to Kalman filter and the Hart equation of Kalman filter. So this is the Hart equation for Kalman filter. Yes, K values are stored in algorithm. So K values are stored in algorithm. All these values are stored in algorithm. So you are going to have an array of numbers where you are continuously updating the values of k, you are continuously updating the values of z, you are continuously updating the values of x hat. So it's basically part of the algorithm. Okay, any questions here? Because the next part will get into the very detail of Kalman filter. Yes. Now what I'm going to do is I'm going to rewrite. This equation is so important. This equation is so important that I am going to rewrite this equation in big red. So this equation is x hat of k is equal to k multiplied by z k plus 1 minus k multiplied by x hat k minus 1. And please note, this is the Kalman gain, which is changing at every step. That is changing at every step. This measurement, you are getting new value at every step. Value at every step. And this is the estimate wherein this is the previous estimate. So every time, every step, this gets updated every step. Now, as you can see, everything is changing. So how does the measurement change? So measurement change from the actual sensor. You have the sensor, and that is the only thing that you are receiving. So I just want to tell you, think about the example that we talked about. You have this light source, and that is changing. Its intensity is flickering, but the only thing that you are able to measure is the output of this LED, or output of this diode, or output of this photoresistor. And maybe the output is voltage. So the only thing that you have access to is this voltage measurement. And what you're doing is you are estimating the process variance. This is something like you estimate. It's very difficult to measure the process variance accurately. So you actually start with some approximation. Sensor variation or sensor noise, you can have a reasonably good estimate or understanding. You can do some testing, or you can use the manufacturer's data sheet and see how well or how bad the sensor performs. Now, my question to you is, tell me logically, how would you change value of k? So for an example, as you can see, in this particular case, k can vary from 0 to 1. So I'm going to call k can vary from 0 to 1. And now my question to you is, can you tell me logically when k should be 1 and when k should be 0? So when kk will be 0, and when kk is equal to 1? So can someone tell me, when would I set kk to 0 and when would I set kk to 1? And this is a very fundamental question in understanding the Kalman gain update. Anyone wants to say, okay, yeah, percentage? Anything else? Anyone else? If you want, you can raise your hand, or you can add your comments in the chat window. So let me say, when kk is going to be 1. When kk is going to be 1, this equation, I want you to see this equation. This is very important. This equation becomes xk as zk. That means kk is going to be 1 when I know my measurement is very accurate. So if kk is 1, I want you to look at the heart equation, and I'm going to draw a heart here because this is the equation that is at the heart of the Kalman filter. So at this heart equation, you will notice kk is equal to 1 when I know my measurement is very accurate. And I don't trust, and I do not trust my old estimate. Old estimate. So which is x hat k minus 1. And this is ck. Now, when would the kk be 0? So when kk is 0, my equation is going to become x hat k is equal to x k minus 1. What that means is exactly the opposite. When I know, when my estimate is very accurate, and say my previous estimate, I need to be clear, when my previous estimate is very accurate, which is x hat k minus 1, and I do not trust my measurement, which is ck. Everyone agrees with this logic? I'm looking at chat window. So does this argument make sense? So now let me ask you this fundamental question related to trust. How do I find out if something is trustworthy or not? Trust is, in terms of digital signal processing, it's actually a mathematical number. So what we are going to do is we are going to see that at every iteration, what exactly is going on. Whether you are estimating, your estimate is correct or your measurement is correct. So now what are the steps to come up with a Kalman filter? And as you can see, please understand, Kalman filter again is a recursive algorithm. What it means is it's gonna compute something, continuously go back and update it. And this update procedure is going to continue infinitely. So this is a recursive algorithm. These equations are implemented in a for loop and they continuously go on. So we talked about why do we need Kalman filter? We talked about Kalman filter mathematics, combining two different density distributions, the actual process, and the Hart equation. So now the next few steps, I'm going to set up the equations for Kalman filter. And then I'm gonna solve a very simple Kalman filter problem. I mean, very, very trivial Kalman filter problem, with the hope that it will make our understanding of Kalman filter super simple. And believe you me, it took about a decade for me to understand the heart of the Kalman filter. Because when I saw these equations, honestly, those equations look scary. And the math or the derivation in Kalman filter is actually super scary, but application is not. So what I'm going to do is, first and foremost, I'm going to write down the equation in discrete domain. So the idea is xk, this is the discrete case. Xk is a multiplied by xk minus 1 plus b multiplied by uk plus wk minus 1. And I will explain it to you what these values mean. This equation is the discrete implementation of x dot is equal to ax plus bu plus some noise. And if you look at MATLAB usually does the implementation in the discrete. So we don't have a continuous signal in a true sense. What we have the snapshots of the continuous signal. So we have this. So we have these snapshots of the continuous signal. But as long as these snapshots are super close to each other, then we have a continuous representation. So what this is the current value. This is the previous value. This is current controller, control input, and this is the noise. And why this noise is coming in the picture? Because that is the fundamental need for the Kalman filter. If this noise would not have been there, if the process noise would have been 0, then maybe just a simple filtering would work. But this noise, this process noise, makes life super complex. Now, what are we getting from here? So we are getting the value of the current state. So this is my output, in a sense that output that is calculated by this equation. So I'm going to call this result. So this is the result. And what I want to do is, I want to convert this result into a measurement, which is h times xk plus, again, the measurement has some noise. So this is the result from equation 1, result from equation 1. And this is measurement noise. And now just to give you an idea, why do we need this H? And what is this A? A is exactly same as the system dynamics equation. So in the case of spring mass damper system that we studied in last class, we had 0, 1, minus 1, 0 as A. So this was our A for a spring mass system. Where stiffness is 1 and mass is 1. Now, what is this H? H, nobody has prevented us from making H is equal to 1. So it is possible that H is equal to 1, which means whatever is the result, only thing is that result is observed. So let me explain this in the context of the example that we have. What we are trying to measure, and this is super important, what we are trying to measure is the light intensity. But unfortunately, light intensity cannot be directly measured. So what we have is we have a photodiode. And what does this photodiode do? The resistance of this photodiode changes depending upon the light intensity. So this is the photodiode. This is the actual light source that has noise, WK. This is the photodiode. That has noise, VK. And now what I'm interested in is I'm interested in knowing the intensity. So my intensity is Z. But the actual measurement, what I'm getting from this system is voltage. And that voltage is XK. And I know that some smart person has derived a relationship between ZK and XK. So ZK is about 3 times XK. So this is something that has been derived. So in this particular case, what I'm interested in ZK, but the value that is being computed from this system is XK. Now, some of you may ask me, wow, how do I get this XK? XK is voltage, or for that matter, it could be current. So let me just put it like current, because I think current will be easier to explain. So just imagine this is current. And we have a constant voltage. So voltage is constant. So I know, and this is very important, XK, which is current, is equal to voltage divided by RK, which is the resistance. So this is Ohm's law. And this RK is changing. VK is constant. So now, if you look at the system dynamics equation, and this is super important, and I want you to understand this, the system dynamics equation for this particular system is going to be XK is equal to, this is something that is being measured, V divided by RK. And again, what you can do is you can rewrite this equation in terms of 1 over some quantity, and then write down the recursive equation. And then this ZK is gonna have some measurement noise, VK. And this X measurement is gonna have some process noise, WK. So boom, this is what we have for our equations 1 and equations 2. So this is equation 1 and this is equation 2. So this is equation 1 and this is equation 2. So the question is, how do I estimate the super duper accurate value of my state and my actual measurement when I know that my measurement ZK is noisy and my state, initial state, the light source is noisy. So I have this process that is noisy. This is again process, and this is measurement. So this is the problem. So first and foremost, what I need to do is I need to come up with the mathematical expression. This is the fundamental difference between the Kalman filter and a complementary filter. Complementary filter does not have an underlying dynamical equation. So it does not have the equation or the dynamics equation, but the Kalman filter needs to have an underlying equation. So once you have all that, first and foremost, step one is build a model. So this model and I will repeat this equation just for clarity. It will be x k minus 1 plus b u k plus w k minus 1. And this is the system model. And then you are going to have a measurement equation zk is equal to h xk plus vk. Wk minus 1 and Vk are the noise parameters. Now, A, B, H, they are the matrices that come from the system dynamics and the measurement equation. But one thing that you want to keep in mind, and this is the fundamental building block of Kalman filter, that the better you estimate these noise parameters, so you have better estimation, better estimation, better results. So what it means is I need to know what is the distribution of this noise, and I need to know what is the distribution of this noise. So if you have better estimation on these noise parameters, your Kalman filter is going to work very accurately. Now, step 2 is this iterative process. So step 2 is this iterative process. Now, there is something called as the time update. So please understand, we have a dynamics, which is like time, and we have a measurement. This is measurement. And this dynamics time is getting updated. In other words, your light is flickering and your measurement is getting updated, which means your output of the resistor is changing. So what I'm going to do is I'm going to write this step in 2 parts, and I want you to follow this. There is something called as the time update, which means you update the dynamics, and there is something called as the measurement update. Time update is associated with equation 1. Measurement update is associated with equation 2. So what happens in time update? And in time update, first and foremost, this is very important. You are going to have the equation for dynamics. This is this equation, and I need to be clear, this is hat because these are estimates. X hat k is equal to a x hat plus b u of k. And there is a concept which is called as prior. Prior means that, so if you look at the estimate, okay, estimate, there is something called as prior and posterior. And what happens in between prior and posterior is you get a measurement, you get a correction. So you have an estimate that you estimated prior to getting correction or an update, correction or an update. And then boom, all of a sudden, somebody tells you, hey, your prior update, a prior estimate is not so correct. Here is the correction that will make your estimate better. And then you have a posterior estimate. So in between these two, you get some input from someone. So for an example, you say, I think my value should be 10, but wait a second, your friend comes to you and says, no, I actually measured it, it's 11. So what you do is in next iteration, you subtract or you add +1, and that becomes your posterior estimate. So what I'm going to do is, you have something called as PK. So this is P. This is A, P, K minus 1, A transpose plus Q. Now, some of you may ask me, what is this P, Q, and R? So just understand that P, Q, and R, these are the values that they correspond to the characterization of noise. And estimating these values, P, Q, and R, it depends upon a lot of factors. So you have something called as this P is called as error covariance. And then you have something called as Q, that is actually the value of the noise. So noise covariance. Now, what do I mean by covariance? Covariance means it kind of tells me that whether a particular quantity is correlated or not, which means are they moving in the same direction or are they moving in opposite direction? So what is the way they are moving? And this PK, just like the prior and posterior, you have something called as the prior covariance. So what we are trying to do is, at every iteration, we take previous error covariance. This is the previous. And we are finding the prior error covariance. And A, this A guy, it's same as this. A transpose is transpose of A. Now the next part in measurement, you have this, the most important thing that we use in our Hart equation is the Kalman gain. This Kalman gain Kk is computed from Pk H transpose H P K H transpose plus R inverse. I'm not going to derive this, but bear with me. I will work out a problem with actual numbers. So again, what you have is this error covariance plays a super important role. This error covariance plays a super important role when we actually look at this PK or computation of Kalman gain. Then first we find the Kalman gain. So this step is determine Kalman gain. The next step is update the estimate. So you have X K hat is equal to the prior estimate. So this is where your prior gets converted to posterior plus, watch out here, here comes the Kalman gain, and Zk minus HXK posterior. This is prior. So now what is happening is this equation is updating state estimate. And the last step is updating the error covariance. I minus KK H P K. So this is updating error covariance. Now that was a lot. So now again, whenever you see hat and dash, it's prior, and then what you're gonna do is this Kalman filter is going to go back and forth, back and forth. So you're gonna have a measurement update that will be used in time update, and then the time update will be used in measurement update. And this process will continue. And every time it's gonna give you an output x hat k. So what comes out of this whole process is x hat k. And once you know x hat k, you can find zk. So at every step, you can actually estimate the state, and you can actually compare that with the measurement that you are getting. So everyone understood, or is it very confusing? So let me take a simple example. And what I'm going to do is I'm going to take a very simple example, and please work this problem with me. That way you will understand how this process works. And this is a very, very common problem. So for example, here is the question. I want to measure voltage that is varying, which is noisy, with a voltmeter that is also noisy. So how do I do this? How do I start this problem? So first and foremost, what we have is we have just one dimensional problem. So what I'm going to do is I'm going to have this one dimensional problem, and I'm going to write this equation. And what I'm going to see here is, let me give you the values of the measurement. So what I do is, and it is super simple to implement this in MATLAB, and you will be surprised about how accurate results you get. So I have time, and I have the value voltage that is measured by this voltmeter. So this is not the true value. This is the measured value. So this is measured. So which means this value has a process noise built in and the measurement noise built in. So let me give you the time at first time step. This is the second time step. This is the third time step. This is the fourth time step, fifth time step, and sixth time steps. So the value goes from something like 0.39, 0.50, 0.48, 0.29, 0.25, and 0.32. And I will just give you the next values if you want. And I would strongly encourage you to actually use these in some sort of MATLAB simulation. So at 7, it is 0.32. At 8, it is 0.48. At 9, it is 0.41. It is 10, 0.45. Now, what I want to do at this point is I want to propose a race. And let me see how many of you are up to it. I have given you a scalar, or I've given you a scalar at time 1, time 2, time 3. What you can do is you can actually plot this value using MATLAB. Okay, you can plot this value using MATLAB. And I want you to feed this value. I want you to feed this value to your Kalman filter block and get the output. So what I'm going to do here is I'm going to work out the Kalman filter by hand, and let me see how many of you in the time that we have, what, 15-20 minutes, can build a Kalman filter block and then find me the output of the Kalman filter. So you should be able to tell me the output of the Kalman filter from the Kalman filter block. So let's go. So first thing I want to tell you, this is a very scalar equation. So I'm going to write down the time update, and I'm going to write down the measurement update. Okay. How many of you are racing with me? Please raise your hand. Not a single student? Nobody wants to give it a shot? Just raise your hand if you are in the race. If nobody is in the race, I actually win, right? Anyway, just try. So I would encourage you to open MATLAB, open Simulink, open Kalman filter block, and then feed this scalar. You can actually feed this through a constant unit and then send these values to the Kalman filter. It will be fun. So as you can see that, okay, yeah, 1. Anyone else? So first and foremost, I'm going to start with my Kalman filter gain at 0. So I'm going to start with my Kalman filter gain at 0. I'm going to start with some initial values at 0 because I don't know. I'm just going to see I'm going to say, let's assume my initial value is equal to 0. But what I want to do is I want to introduce some noise. So deliberately, I'm going to assume my noise at P0 is equal to 1. And remember, this noise covariance comes here. I'm going to say my P0 is equal to 1. So what I'm going to do is I have two equations, the time update and the measurement update. So since I'm doing no dynamics at all, what I'm doing is I'm just measuring my update equation is going to be very simple. Xk prior is equal to x hat k minus 1. So this is the posterior in step k minus 1 becomes my prior in current step. Okay, I just have 2 students competing with me. Anyone else? Let me see. Let me pick someone. Isabella, Alejandro, Brian, Jacob, Jade, Michael. I have 2 Michaels. So Joseph, just give it a shot, because then you will understand the nuts and bolts of Kalman filter. Next step is, and then I will once, if you get good results, you can share your results with the class. PK, it will be a highlight of my day if you can get it done. Okay, so please try it. So yes, you have to put it in an array, and you have to feed that array to your Kalman filter block. So what you're going to do is you actually create this in an array and send value one by one to your Kalman filter block. So Pk is equal to Pk minus 1. And this is very simple because there is nothing. This is just a very simple equation for time update. Now, what happens with this measurement update? In my measurement update, the first step is finding out the Kalman gain. And this big equation for Kalman gain for this simple scalar value gets converted, I want you to check this. This becomes pk prior divided by pk prior plus r. And some of you may ask me, ooh, what happened here? Can you see that this guy is actually inverted? So if you have a matrix, I would have a matrix inversion. So that's why you have this matrix inversion. But here it's a scalar value. So it is just 1 divided by that value, because this is just one single number. Next thing is xk. This is going to become my xk prior plus, don't forget the Kalman gain, kk zk minus x hat k prior. And the last but not least, pk is equal to 1 minus kk pk. Now what I'm going to do is, here is what I'm going to do. I'm going to take this value as my first value. I will, by hand, I will calculate this iteration. So I'm going to do this whole iteration by hand. And I hope with powerful software like MATLAB, you'll be able to get answer quicker. So some of you may ask me, wow, so what do I put in the matrices for Kalman filter block? In your Kalman filter block, you have to put A is equal to 1, B is equal to 0. Then obviously you are going to have C and D. You don't need to put because there is no direct update from the sensor. So you can actually uncheck the block on the update. So input update. So let me go ahead and do this calculation by hand. Okay, so I'm going to show you this calculation. So this is the value of k. This is the value of zk. This is the value of xk minus 1. This is the value of pk minus. This is going to be my time update. This is going to be my measurement update. And this is what I'm looking for. And then this will be my pk. So I'm going to fill this table. And first iteration is k is equal to 1. What is the value of zk? Zk, the value that I measure is 0.39. And everyone, please pay attention. This is the simplest way Kalman filter can be explained. So I want you to follow this iteration, and I want you hopefully to get the similar results from MATLAB. So now xk minus 1. So to begin with, I don't have any estimate. So I don't have any estimate. So when there is no estimate, I'm going to start with 0. I know that I started with pk is equal to 1. This is something that I assume. So these values are assumed. So I assume. Now my time update is x k hat prior is equal to x k minus 1. So xk minus 1 is 0. So which means my x hat prior is going to be 0. Next step is my pk prior is going to be my pk minus 1. And what is my pk minus 1? My pk minus 1 is 1. So I get pk bar. Now my measurement update, and please follow this very carefully. First iteration is getting the value of Kalman filter gain, which is 1 divided by 1. So 10. So 1 divided by 1.01. So let me explain here. So pk is 1, and I'm going to assume my r value to be 0.1. So I get this value. So this is 0.9 xk. So if you look at the calculation here, it's going to become, so next step is finding out value of x k is kk 0.9, 0.39, which is zk minus the previous 0. So my xk has become 0.35, and my pk has become 1 minus 0.9 multiplied by 0.1, which is the value of r, and that becomes 0.09. So this thing becomes 0.09. Now here comes the next question. So what do I get at xk? Xk going to become 0.35, and pk is going to become 0.09. Now I want you to see the power in the very first iteration. This is super important. My measurement was 0.39. I started with 0, but with this mathematical algorithm, my estimate happened to be 0.35, which means even if I start with a wrong guess, I started with completely off guess, x is 0. In my first iteration, I got a result which is close to the measurement. I don't know if it is super accurate, but let's see what happens in the second iteration. In second iteration, my measurement becomes 0.5, this 0.35. This guy comes from here. Then pk becomes 0.09. In my time iteration, I'm just gonna give you I'm gonna write this equation down. Xk, which is going to be 0.35. This comes from here, and my pk xk and pk is equal to 0.09. This guy comes from here. Now in the measurement update, this is a little convoluted, so please pay attention. Step 1, find out the Kalman filter gain. 0.09 divided by 0.09 multiplied by actually plus 0.1, that gives me 0.46. xk becomes 0.35 multiplied by 0.47 multiplied by, there's a multiplication, I'll write this over here, 0.5 minus 0.5 comes from here, 0.5 minus 0.35. That gives you 0.42. Now, as you can see that your measurement is 0.5 and Kalman filter is getting 0.42. So xk here becomes 0.42. And then last step is finding out pk. So pk becomes 1 minus 0.47. Actually, this should be 0.46 here, just to be clear. This should be 0.46 multiplied by 0.09, and that gives me 0.048. And this guy becomes 0.048. And if you continue, I'm just gonna give you the values: 3, 0.48, 0.424, 0.048, 0. This is the third, 0.442, 0.032. If you look at the fourth step, you're gonna get 0.29, 0.442, that is the measurement, 0.032, 0.405, 0.024. And I can continue on. So I'm gonna write down in the fifth iteration. The fifth iteration, so ck x k minus 1 hat pk prior. This is where you have the measurement and time and measurement. I will not give you updates here, but I will give you the updates xk and then pk. So in 5, you are gonna have 0.25, 0.40, 0.02, and the answer is going to be 0.37 and 0.02. In 6, you're gonna have 0.32, 0.37, 0.016, 0.032, 0.014. And I'm gonna give you these values in the chat window, so you have those as reference. So please note the first value is zk, xk minus 1, pk, no time, no measure. This is xk, and this is pk. And then at the end, if you were to plot, you will notice a very nice graph. You will see that your Kalman filter value will be something like this, and it will converge to a certain value, and this converging value is 0.4 is the value that you should be getting at the end of the convergence. So the true value is 0.4 in 10 iterations. So as time goes on, what I want you to do is I want you to plot x hat And that is how the Kalman filter should get. And once again, once you know steps from here all the way up to the hand calculation, all the way up to this, you know the nuts and bolts of linear Kalman filter. And I will talk about the extended Kalman filter and unstinted Kalman filter in next class. And then we will see how these can be implemented for our UAV problem using sensor measurement. I'm gonna stop recording